Okay, today is Monday, December 12th. Sorry I can't be with you guys today. They'll have one more day of testing, so I'll be back on Tuesday. So, reversible and irreversible or not reversible reactions. What happens when chemical reactions do not go through completion? Our learning intention, we will understand different types of reactions and the impact external changes can have on those reactions. And your success criteria, I can identify and describe reversible and irreversible reactions. I can describe static and dynamic equilibrium systems. So this goes along with what you've been working on from last week. What last week's assignments talked us about equilibrium. So this is just an extension of that. All right. What happens in a reaction goes if a reaction goes to completion? That when enough of both reactants present, the reaction go to completion, there is at least one of the reactants is completely used up, so it's no longer available to continue reaction. So often, however, chemical reactions do not go to completion. A reaction that doesn't go to completion is often reversible. A reversible reaction is one in which the reaction can occur both ways. The reaction can react to form products, call that a forward reaction, and the products can be reverted back to the original reactants we call reverse reaction. When the rate at which the forward reaction is equal to the rate at which the reverse reaction, then we call the reaction in reached equilibrium. When the reaction is reversible and can reach equilibrium, we use the symbol. So the yield symbol has a forward and a backwards to it. So it's kind of like half an arrow. All right, so what you're going to be doing there's a Nearpod assignment where you're going to watch some video and record your observations, determine whether the experiment was completion or reversible or not. So that one is a separate assignment, but it looks like this. Okay, I'm going to, you can't hear this, so I've broken this up into pieces so that it's easy to do. I'm going to skip this one. Save this. Okay, so let's just go on to the next slide. All right, here we go. So there are open versus closed systems. Open system energy and matter can be transferred into the surroundings, and your video will show you more about that. Energy is transferred. So what's the same for both? Energy can be transferred out of the system. So if you put something in a closed system, it means that they can't. The energy, the materials going in can't come out, but you can get heat out. You can get that. So energy and matter are transferred to the environment or the surroundings. And what they have in common is even though you have it open and can go out of the environment, the energy can be transferred. So everything, the matter itself, the materials, the reactants, stay in a closed system. All right, what is equilibrium? Consider the following reaction. Reactant 1 plus reactant 2, and there's the equilibrium sign, product 1 and product 2. At the first, the rate at which the forward reaction takes place is going to be much faster than the rate of reverse reaction. This is because the beginning of the reaction, there are more reactant particles than then product particle. Once a particular concentration of product is reached, the reverse reaction will start to occur. Once the rate of the forward reaction equals the rate of reverse reaction, we call this equilibrium. So here is the dotted line shows the forward reaction. So starts with the product or the reactants, and you have all the reactants. So this is a certain number, and then you start losing. It starts going away and becoming products, and you can see the product is in the bottom here. So we start with nothing, and then we get to a middle point where they match. So this is what they call the equilibrium. The forward and the reverse match each other. So when reactants are becoming products, that's the forward. And when products are becoming the reactants, that's called the reverse. At this point, the concentration of the reactants and the products do not change. They remain constant. For example, imagine walking up an escalator, traveling down. If you walk at the exact same speed the escalator is traveling down, you will remain in the same place. You will still be walking up, escalator is still moving down, but you remain in the same place. So system equilibrium over time. So here is equilibrium is reached. The same amount going forward is the same amount going in reverse. Equilibrium can only be established in a closed system. This is because in an open system, some of the reactant or product may be lost, or matter may be transferred into the system and disrupt the reaction. If the system is closed and has reached equilibrium, we should not observe any of the following: changes in macro visible properties of the solution, color, state, which means the precipitate forming, changes in volume, gas volume, changes in smell. Look familiar? These are the signs of a chemical reaction. Static versus dynamic equilibrium. Static equilibrium is where there's no movement between the reactants and product. It is said that the reaction is at rest and the rate of the forward and reverse reaction is 0. Dynamic equilibrium is when the rate of which the reactants are converted to products equals the rate at which products are converted back to the reactant. This is happening constantly in the system. For a reaction to set up a dynamic equilibrium, it needs to be both reversible and a spontaneous reaction. An example of a static equilibrium is the conversion of carbon in the form of graphite to carbon in the form of diamond. While the reaction could be reversed, it reaches a point at which it will no longer continue and cannot reverse unless large amounts of energy or pressure are applied. Diamond must be heated to approximately 2000 degrees Celsius before the reaction will reverse and convert the diamond to graphite. So if that isn't happening, then no diamond is being converted to graphite, and vice versa. This process, therefore, is static equilibrium. The rate of forward and the reverse reactions are 0. Another reason the system might reach static equilibrium if it runs out of one of the reactants called the limiting reagent. If there is no more of one of the reactants present, then the forward reaction can no longer take place. Therefore, the system reaches static equilibrium, and again, the rate of the forward and reverse is 0. An example of a dynamic equilibrium is a sealed bottle of a soft drink. The rate at which carbon dioxide escapes the solution is equal to the rate at which it dissolves back. So here's the equation: H2O plus CO2 gives you H2CO3. Undissolved gas particles, carbon dioxide, the rate of the CO2 escaping is equal to the CO2 dissolving. So again, this is a sealed solution, sealed system or closed system with a cap. You know what happens when you take the cap off, your soft drink goes flat. So check your understanding. What is a closed system? Go back one here. Closed system, what's a reversible reaction? Explain why the reaction of magnesium and oxygen form a magnesium oxide. So these are the things that you're going to do in the Nearpod assignment. All right, so that's all we have for today. And I will see you Tuesday.